Okay, my name is Lejeune, and I am the lead for next week's lab, internal combustion engine performance. As you can see from this diagram, this is your normal reciprocating engine, 4-stroke, and just one cylinder. So the experiment, we're looking at engine performance, different parameters under different engine loading conditions. Constant speed, variable load, and constant load, variable speed. These are good ways to see what each has, how each affects the engine performance while holding the other thing constant. So, internal combustion engines. First off, reciprocating or rotary. Rotary engines are really not very common. They're found in a couple of road vehicles, namely Mazda's RX-7, RX-8. But I'd say that your normal internal combustion engine, probably over 95% are reciprocating. Ours is just that, reciprocating. Also, there's 2 or 4-stroke motors within reciprocating engines. 2-stroke are found commonly in rather small engines, weed eaters, some lawnmowers, you're going to have 2-stroke engines. They have fewer moving parts, but they're rather convoluted, and also normally you're going to have a mixture of gasoline and oil when you're running it. The one we have is a 4-stroke. Pretty much every motor vehicle is going to have a 4-stroke engine. More moving parts, but they're more efficient and less things can go wrong. And also, spark ignition or compression ignition. Most of your diesel engines in vehicles are going to be compression. They're also going to have a much higher compression ratio, and that's what makes that possible. In this instance, we have spark ignition, and it is a gasoline engine. The vast majority of those are spark ignition. So here's a little diagram of the different 4-strokes. First is the intake. Your intake port here is going to be open. The piston is moving down to bottom dead center. And this is your air-fuel mixture is going into the engine. Then on the compression stroke, you're moving up towards top dead center, and your air-fuel mixture is being compressed. At the top of that, you'll have a spark, which causes an explosion, which causes your power. This is your power stroke here. That forces it down. This is the only stroke that creates power to move the crankshaft. And then after that, your exhaust port is opened, and the piston will move up and expel your used up air and fuel, whatever fuel is left in there. So, specifications for our engine, it's a 13 horsepower overhead valve single cylinder engine. 13 horsepower is pretty good for just a single cylinder. And also it'll be connected to a land and sea dynamometer. This creates the amount of load you have on the engine, and it measures torque, which can be used to compute horsepower as well. Uses 87 octane gasoline. If you go to a gas station, that's your base model gasoline. And then air density and a couple of conversion factors here. Some equations we're looking at. Air mass flow, this has to do with the air-fuel mixture. And then a number of efficiencies. These are just different ways to calculate the power you're getting out of the engine as compared to what you're having to put in. And then brake mean, effective pressure right here, and power. Just a few more things to compute. Safety information, it's important to note that spacebar will kill the engine. If things start flying or if something goes terribly wrong, you can spacebar and kill it. There's multiple carbon monoxide sensors in the lab, which is right over here. And if the fan is not on to make sure that the used gases are going out and not staying where we're at, you might have a problem. Carbon monoxide can kill you, so if those things go off, get out of there. Also, there's explosions going off, so you have hot parts, and then also it's moving a shaft, which means you have a bunch of moving parts, so don't touch the engine. And we will have aeronautic protection, make sure you're wearing that. The procedure, first you're going to initialize the lab. Set up everything that needs to be set up, make sure that fan's running for the exhaust fumes. Then to start the engine, this can be done on the software. Run the tests and collect the data. All of this is run on the software, and there's a much more detailed procedure in the lab manual to show you just how to do that. So the Otto cycle, this is what the engine runs off of. On the bottom here is the ideal cycle, and on the top is our cycle. So one of the major differences in the ideal cycle, you simply have heat in and heat out. That's not possible in the real world. So there's going to be a lot of inefficiencies in here. And some of these things, mainly due to heat losses. Heat losses are the number one contributing factor to the lack of useful power to be formed in this process. Also, there's work required to intake and expel the gases, and this is not true ideal gas behavior, especially when you have explosions. It's not going to behave ideally. All of these things contribute to less efficiency and non-ideal behavior. Okay, the water brake dynamometer, the water in and water out is what determines the load on the engine. This right here is connected to the crankshaft, so this is turning by the engine. And the torque is measured as an output from the dynamometer. A lot of people have probably seen cars get hooked up to the dyno, which is pretty much the same thing. Except this one requires a little bit less setup. So the performance, we're looking at the engine response to different conditions. Again, constant speed variable load, constant load variable speed, and see how that affects the engine. Power and torque. Power is simply dependent upon torque and RPM. If you're looking at power in units of horsepower and torque in units of foot-pounds, then here's your conversion right here. And what this means is if your RPMs are 52, then horsepower is equal to torque. If your RPMs are less, torque will be higher. If RPMs are greater than that, horsepower will be higher. And here's just a simple curve to show that. Right here where they meet is going to be roughly 52 RPMs. And the shape of these curves depends on the engine performance. In most motor vehicles, your torque is going to peak up here early, 2 to 400 RPM to 4,000 RPM. And your horsepower, again, it's going to peak later on, and it's going to be higher than torque at 52. Any questions?